So guys, our Wellsharp course supervisor level course objective. Number 1 is to increase candidate operational knowledge of well control procedures and killing operation. Number 2 is to prepare candidate for Wellsharp surface well control examination. So if we're gonna talk about our course, so our course is divided into 2 main parts. First part is PMP, principle and procedure. Second part is equipment part. So for the first part, principle and procedures, we're gonna talk about key principles like a kick, a blowout, okay? How to prevent a kick, how to prevent a blowout through a barrier. So we're gonna talk about the barrier categories, the barrier classification, and how to make pressure test for the barrier and what is the type of the pressure test. Then we're gonna talk about the main pressure in our course, hydrostatic pressure and formation pressure. Then go ahead for the reasons for the formation pressure to be abnormally pressured. Okay. Then we're gonna talk about the circulating system. We're gonna talk about the bottom hole pressure in case we are in a static situation, no circulation, no pumps running, and the bottom hole pressure in the dynamic situation in case we have pumps running. Okay. Then we're gonna talk about the pump pressure and its relation with the change in the pump speed, or pump pressure and its relation with the change in mud weight. Okay, so changing mud weight or changing pump speed have. Okay, so the one who asked for the exercise book, I'll ask IMX to forward you this material and the break. Okay, so don't worry. Yeah, don't worry, guys. This material will be sent to you. Okay, so let's go ahead. For the pump pressure and its relation with the change in pump speed or change in mud weight. Okay, then we're gonna talk about the kick warning signs. Okay, while drilling operation, while tripping operation, or making a connection, you may, yeah. Okay, guys. So all of you didn't receive the exercise book, so I'll ask IMX Center to forward you this material. Don't worry. Okay, and the break they're gonna forward you this material. Okay. So let's proceed ahead. We're going to talk also about the kick warning signs. Okay, while drilling operation, while tripping, while making connection, there may be some signs if we notice. So this may be indication of a kick, or this may be for sure you have influx. So for sure you have a kick and you need to shut in the well. So in case we have a kick, we need to shut in the well. So this will be the next point to talk about. We're going to talk about shut-in methods. Okay, we have 2 methods: hard shut-in method, soft shut-in method, according to the company policy. Okay, after shutting the well, we need to record some data. So we're going to talk about the recorded data after shutting the well. Okay, then going to talk about the gas behavior inside the well. We have 2 types for the behavior. We have gas migration and gas expansion. Okay, so we're going to talk about this one, then finalize our first day by talking about what, as mentioned, about the gas migration, about the gas expansion, gas behavior at all. Then we're going to talk about special cases like if we are in a horizontal well. Okay, if we are in a horizontal well. This is for the first day. For the second day, we're going to complete our PMP part, talking about kill sheet, how to properly solve kill sheet, then talking about killing method. Okay, we have routine method like driller, weight and weight, and we have unconventional like volumetric method. So we're going to talk about all of them. Then we're going to talk about stripping operation. Let's say also kick tolerance phenomena like plowing, okay, plowing effect. Then gonna talk about gas hydrates and the drills or training being conducted in the oil field to ensure that the crew is competent enough so they can react and deal with the kick situation properly. Okay, that's all for PMP, first day and second day. Then for third day, we're gonna have equipment parts. So we're gonna talk about the BOP stack, its arrangement, annular, and the RAM. Okay, then talking about pressure test, the tools used for pressure testing. Then talking about for surface control system, COM unit, and its components. Okay, then talking about also the diverter and finalize the equipment part, talking about the connection, the flange and ring gasket types. Okay. Also at the third day, we're gonna have simulator training, and we may pass about the new part added this year to the Wellsharp course, MPD. Okay, managed pressure drilling. This part is new part to the Wellsharp. Okay, so it has some questions new to the course. So we're gonna discuss with you this part. For the last day, the fourth day, we're gonna have a simulator assessment and we're gonna have revision. Okay, so let me mention about our exercise book. Our exercise book is very, very important. Okay, the exam will come typical like these questions. So we need to solve these questions properly. And the exercise book, we have model answer. So you can check your answer with the model answer. Okay. As mentioned, the exercise is very, very important. All of its questions will come in the exam with the same number, with the same choices. Okay. Also, we have at the last some quizzes. These quizzes is typical like the exam. Also, our exercise book included 4 kill sheets. Okay, 4 kill sheets. One of them will come in the exam with the same numbers. So it's very important to practice it carefully. Okay. Yeah, I think that's all for our exercise book. So just pay it your attention as it's very, very important. Coming here to the course outline, as mentioned, day number 1 will be principle and procedure. Day number 2 will be continuing for principle and procedure. Day number 3 will be well-controlled equipment and virtual simulator training. For day number 4 will be revision and quizzes and virtual simulator assessment. For day number 5 will be your final virtual exam. Okay. Coming here to the first part, principle and procedures, first part. So let's talk about these.
Sorry, just a quick question, because it's first time for me to pass ADC. Is
Okay.
this ADC supervisor level is the top level, or
Yeah,
is more level?
yeah, the top level.
Okay. Also about I thought 6 hours starting from 10:30 to 4:30. Yeah.
Yeah, but we may finish the day by this time. It depends on.
We cannot start earlier because.
Yeah, it's now earlier for you.
It can.
Now it's earlier for you.
Not is earlier, but no, I mean if you can start earlier, more earlier.
Yeah, more earlier. Okay, so let's arrange that with you at the end of the day. Okay. Okay, so the course may last for 4 hours if it's okay, more than 4 hours by a little bit, so it's okay, we can handle it. But if you need it to be more earlier, so we can adjust at the end of the day. Okay.
Okay. Thank you.
Okay. So let me just check. You now see my shared screen on overbalance versus underbalance in the full screen. Guys, you now see my screen, overbalance versus underbalance.
No,
I'm seeing well control principle and procedure.
Yeah, okay, good the point. So there is a problem with slideshow here. Okay. Now you see it, overbalance versus underbalance?
Yes.
No.
Yes.
No or yes?
Yeah, overbalance
I cannot.
versus underbalance. Yeah,
Yeah, so now you see full screen, right?
yeah.
Okay. So let's start. This
I
guy,
cannot see it.
you can't see?
No, I cannot.
Okay, so I think it's a problem from your side. All guys, you see now full screen overbalance versus underbalance?
Yes,
Yes,
from
we
here.
can see it.
Yeah, so now I think it's a problem for you from your side. So could you check this issue?
Checking. Because I can see only the logo.
Okay, so what screen you see now?
Now it's saying Ahmed, but before when were you only seeing like a logo?
Logo only? Yeah, I think now
Mhm.
it's a problem of internet or internet issue. So you can just adjust your internet. You're gonna see the page we share.
Okay, let me check.
So now it's okay. We're gonna go ahead. Okay, guys. Is it okay to proceed? Guys, it's okay to proceed?
My side is okay.
Okay.
Yeah, from my side also, but we don't know about the other guys.
Okay, so the one has a problem with the screen. It's okay now to start?
Okay.
Okay. So guys, here, these are the situations we may face during the operation. First case or first scenario, balance situation. If we have here our hydrostatic pressure, the well, okay, is equal to the formation pressure. So we are in balanced situation. The hydrostatic pressure is the pressure exerted by the columns that are inside the well. So this hydrostatic pressure, as long as it's equal to the formation pressure, so we are in a balanced situation. No formation fluid will enter to the well. Second situation, the one we see during drilling operation, is the overbalanced situation. Here we have our hydrostatic pressure is greater than the formation pressure, okay? So preventing any formation fluid to enter to the well. The minimum overbalance is about 200 psi, and this pressure is equivalent to 0.5 ppg. So if we have our formation pressure is equivalent, for example, to 10.5 ppg, so we're going to use hydrostatic pressure equivalent to 11 ppg or 11.5 ppg. Okay. For the last scenario or the last case is underbalance. Once our hydrostatic pressure here inside the well is less than the formation pressure. So the formation pressure is larger than the hydrostatic pressure for any reason. For example, we may have less hydrostatic pressure due to reduction in the column or less hydrostatic pressure due to a sudden jump in the formation pressure to be, for example, abnormally pressure. So in this situation, it will be underbalanced situation and formation fluids will manage to enter to the well, causing the well to flow. Okay, so if look here to this situation, now our hydrostatic pressure is not sufficient enough to overcome the formation pressure. So formation fluids manage to enter to the well. Okay, so now we have a kick situation. So the kick situation is an influx of formation fluid that causes the well to flow. Influx from formation fluid that causes the well to flow. So the formation fluids may be oil, may be gas, also it may be water. Okay, so the water is also considered as a kick, or maybe mixture of oil and gas. As long as the formation fluid inside the well, so it's called a kick. Okay, no migration happened, no movement happened for the influx, so didn't reach the surface yet. But once these formation fluids or the influx manage to reach to the surface, so now we have another case, we have another scenario called a blowout. So what is a blowout? It is an uncontrolled exit of the formation fluid at the surface. Okay, so now formation fluids enter to the well and then manage to reach to the surface. Once the formation fluid reaches to the surface, so now we have a phenomenon called a blowout. Okay, just like as explosion. Okay, so to prevent formation fluids to enter to the well and to prevent the migration and the movement of the influx not to reach to the surface, we need to have something called a barrier. So now let's talk about the well barrier classification. Number one, we having primary well control barrier. The primary well control barrier is the use of the mud, use of hydrostatic pressure to prevent formation fluid to enter to the well. Let's imagine if we have here our well, okay, and now this is our drill string. We are in drilling operation. So as long as our hydrostatic pressure here is greater than the formation pressure, so no formation fluids will enter to the well. Once the hydrostatic pressure is less than the formation pressure, so the formation fluids will enter to the well, causing the well to flow. Okay, so primary barrier is the use of the mud to prevent the influx or the formation fluid to enter the well. Once we lost our primary barrier, okay, so it is time to use secondary barrier. The secondary barrier is when we have influx inside the well, is to close the POP, okay, during the drilling operation. Shut in the well is to close the POP to prevent the movement of the influx, okay, not to reach to the surface. So here, the secondary well control barrier is the use of the POP to control the well if the primary well control can't be maintained or failed. Okay, so what will happen if the primary has been compromised, the secondary has been compromised? So now it's time to talk about tertiary well control barrier. This one is the last option. Okay, so let's imagine if we have here our well. While drilling, we have influx, and this influx managed to reach to the surface. So we have a blowout. Okay, so now our primary barrier has been compromised, our secondary barrier has been compromised. So now it's time to drill a relief well. The relief well is a drilled well in a nearer place like this, directional well. Okay, so you can drill this well and start inject at this well special material or heavy material, junk material into the kicking zone to prevent it from more kicking. Okay, so this is called the relief well, like what happened in Gulf of Mexico. Okay, Gulf of Mexico accident. So primary barrier to prevent formation fluid to enter the well. If it's lost, so it's then to secondary barrier, use of the POP, okay, to prevent the influx from reaching to the surface. Tertiary barrier is a drilled well in a nearer place, okay, it's directional to start pumping the special material or junk material into the kicking zone, so you can prevent it from more kicking. Now we have another classification for the barrier, okay, according to IWCF. So number one here is called procedural or operational barrier. During the operation, monitoring the well for gain or loss is called okay. So guys, here we have procedural or operational barrier. During the operation, monitoring the well, monitoring the bed tank for any gain or loss It's called operational barrier or procedural barrier from its name during the operation. Monitoring the well for gain or loss, it's called operational or procedural barrier. Second type is called physical barrier. Physical barrier from its name, something you can see untouched, like what? Like cement block, like POP, like the mud. Another type is mechanical barrier. So the mechanical barrier is a piece of equipment that contains the flow from formation, like the unperforated casing. So for example, if we drilling our well, okay, to the setting depth, then run our casing, then making cement operation. So now the unperforated casing, this casing, okay, is act as a barrier, okay, against the formation fluids. So now the formation fluids will not be able to enter to the well. Last thing here, we have something called barrier system or barrier envelope. Okay, so what is the meaning of barrier envelope? It is use of more than one barrier acting together in place. So for example, during a normal drilling operation, we have two barriers. We have our hydrostatic pressure, okay, and we have our POP. Okay, so barrier system or barrier envelope, more than one barrier acting together, okay, to control flow from the formation. But let's say, according to the well control recommendation, no barrier can be called as a barrier till passing pressure test. Okay, so here, how to pressure test the well? We have two types of pressure test. We have positive pressure test and we have negative pressure test. So if you look here, if we have, for example, our well like this, okay, and we have here cement block as a barrier. So we have two types of pressure test. First type is positive pressure test. Let's take this cement block here. So there is two pressure acting on the cement block. Pressure from surface side and pressure from formation side. Okay, the pressure from the surface side is the hydrostatic pressure, and the pressure from the formation side is the formation pressure. Okay, so here is pressure from surface side, and here is pressure from formation side. Okay, for positive pressure test, we're gonna allow the pressure from surface side to be larger than the pressure from the formation side. So we're gonna apply pressure from here, from the drill pipe side, from the surface side of the cement block. Okay, applying more pressure from surface side. So now pressure from surface side is larger than pressure from formation side. Okay, and let's say, according to this figure, we increase the pressure, then once reaching to a specific point, okay, we need to keep our pressure constant for about 10 minutes. For about 10 minutes, and notice that the pressure is stable, no leak, no pressure drop. If no leak, no pressure drop, so it's okay, it's accepted test. If there is pressure drop like this, okay, so now the barrier can't be accepted, okay, and it need to be replaced immediately or put another cement block. This is for positive pressure test. So what about negative pressure test? Negative pressure test, if we have the cement block here, same thing, we have two pressures, pressure from surface side and pressure from formation side. So here, vice versa, we're gonna allow the pressure from formation side to be larger than pressure from surface side. So how to make this point? We're gonna make displacement for the high weight fluid here. So if we have, for example, here our mud weight is 9 ppg, and our formation is equivalent to 8.5 ppg. Okay, so we're gonna make replacement for or displacement for the 9 ppg by another lighter fluid, let's say 8 ppg. 8 ppg. So now the hydrostatic pressure in the well will be less than the formation pressure. Okay, so here we allow the pressure from formation side to be larger than the pressure from surface side. And same thing, we need to check for pressure stabilization. Okay, so the pressure now is at this point. If the pressure stays stable for about 10 minutes, so it's okay. If we found pressure build up due to communication from the formation side to the surface side. So now there is a leak across the test block, the cement block, and it needs to be replaced immediately. It is not accepted test. So the difference between the positive pressure test, and negative pressure test is positive pressure test, you apply pressure from surface side larger than or more than formation side. Okay, and you need to check no leaking across the barrier. For the negative test, you allow the pressure from the formation side to be more than the pressure from surface side. And you need to check no pressure buildup, no communication, no leaking across the cement block. So from your opinion, guys, from your opinion, which one is recommended, positive pressure test or negative pressure test? Anyone could share?
Both.
Both. Okay.
Negative.
Yeah, I think which one is recommended? Yes, the negative one is recommended. Why the negative pressure test is recommended? Negative pressure test is recommended because it is in the direction of the flow. So, for example, here, once the cement block can withstand the pressure from formation side, so here pressure from surface, and here pressure from the formation. If the pressure from formation side is larger pressure from surface side, and the cement block can withstand the pressure from the formation direction, so it's okay for us, okay? As if we have a kick, it'll come from down, okay? So the cement block can withstand the pressure from below, okay? So it's okay for us. So here, negative pressure test is recommended to be conducted, okay? Okay, so according to the API, minimum two tested barriers are on place. So during the normal drilling operation, the minimum two barriers, number one is the hydrostatic pressure of the mud. Number two is the POP, minimum two tested barriers. For the well intervention jobs, as we are in underbalance situation, we have well head pressure, so we need three barriers. But for drilling operation, we are in overbalance situation, so we need only two tested barriers, our hydrostatic pressure and our POP. Also here, we need to make pressure test for the cement block and the liner lab. Why these 2 points specifically? Because these points are points of communication with the well fluid. If you look here to the liner lab, for example, like this, if we have leaking across the liner lab here, so formation fluid will manage to enter the well from this point. So we need to make negative pressure test or inflow test or dry test for this point to check no leaking across this point. Also for the cement block, as you see, if we have here leaking across the cement block like this, if we have leaking across the cement block, so formation fluids will enter to the well. So cement block and liner lab, these 2 points are points of communication. So we need to check their integrity by applying negative pressure test to check no pressure leaking or no pressure build up across this point. Okay, now to talk about the pressure concepts in our course, we have two main pressures. First one is called hydrostatic pressure, and second one is called formation pressure. Okay, so here is our hydrostatic pressure, and here is our formation pressure. So here hydrostatic pressure and here formation pressure. As mentioned before, we need during drilling operation to have our hydrostatic pressure is larger than our formation pressure. So we are in overbalance situation. So no formation fluids will enter to the well. So the hydrostatic pressure, as you want to see, equal what? Hydrostatic pressure equal what? Equal 0.52 times TVD times mud weight. Okay, we're gonna see in detail this formula, and formation pressure is the pressure of the fluids in the pore space of the rock. Okay, so let's go ahead and see. For hydrostatic pressure, guys, here hydro means fluid and static, you are at rest. Hydrostatic pressure is the pressure exerted. Okay, so here hydrostatic pressure is the pressure exerted by a column of fluid at the rest. Hydrostatic pressure here equal mod weight times TVD times K time constant. So here's the pressure unit in PSI, pound per square inch, mod weight in ppg, and depth in feet. Okay, so how to convert from ppg? Okay, how to convert from here from ppg times feet into PSI? So we need to have a conversion factor is equal to 0.052. So this conversion factor function is to convert from feet times ppg into PSI, or pound per square inch. For the hydrostatic pressure, we only concern about the TVD, If you look, hydrostatic pressure is equal to 0.052 times TVD times mod weight. So if we have the same mod weight in all of these different shapes, okay, and all of these different shapes have the same TVD, so now we're having the same hydrostatic pressure at the bottom of all of these different shapes, okay? Hydrostatic pressure is only dependent on the TVD, not measured depth, not the volume, not the shape. So here you have to consider the vertical height or depth of the fluid column, not the shape of the hole. The shape doesn't matter. So what is the difference between TVD and MD? As you see here, our well here is vertical and here is deviated well or directional well. Always measure depth is greater than or equal the TVD. So here our TVD is equal to our measured depth, but here, as you see, our measured depth is larger than our TVD. If you look here, both of the wells have the same TVD, 10,000 feet, but here TVD equal MD, same 10,000. Here we have 11,650. Okay, so it will be greater than 10,000. Okay, so during our course, let's mention about something important. The TVD is used for pressure calculations, and MD is always used for volume calculation. Okay, so also during the cal sheet, if we need to calculate for any pressure, we're gonna use TVD. If we need to calculate for any volume, for example, the relistering volume or annulus volume, so we need to take into consideration the measured volume or the measured depth. Here we have another concept called hydrostatic pressure gradient. As you see, our hydrostatic pressure is equal mod weight times TVD times constant. If we divide it by TVD here, so it will be hydrostatic pressure over TVD. So its unit will be PSI per feet. Okay. So now it will be hydrostatic pressure gradient. So the hydrostatic pressure gradient equal what? Equal mod weight times 0.052. So we can write the equation hydrostatic pressure equal hydrostatic pressure gradient with unit PSI per feet times TVD. Okay, so what is this meaning? For example, if we have here a pressure at the end is, let's say, 3 PSI. Okay, and we have here 6 feet as TVD. So to get the hydrostatic pressure gradient, just take the hydrostatic pressure and divide it over the TVD. So for this example, we have hydrostatic pressure 3 psi over TVD 6 feet. So our hydrostatic pressure will be 0.5 ppg. Okay, guys, that's all for hydrostatic pressure gradient. If he, for example, give you mod weight, okay, mod weight, and asking for the gradient. Let's write this equation again. Hydrostatic pressure gradient equal what? Equal mod weight times constant, 0.052. So if he give you mod weight and asking for the hydrostatic pressure gradient, you need to multiply the mod weight by the constant. If he gave you the hydrostatic pressure gradient and ask for the mod weight, so you need to divide the hydrostatic pressure gradient over the constant. Okay. Okay, so now let's talk about the formation pressure. Formation pressure, let's say our formation pressure is 3000 psi. So what does this mean, guys? Anyone could share what does mean about formation pressure equals 3000 psi? What does this formation mean?
Pressure in the wellbore is 3000.
Okay, thank you. Okay, so this pressure is the pressure. Okay, yes, okay. So this pressure, guys, is the pressure of the fluids within the pore space. For example, if we have our well like this, okay, and we have here our formation fluid, let's say gas, for example. Okay, so the pressure of this gas here is 3000 psi. If we take a kick at this point, so the pressure of the gas will be 3000 psi. The gas will enter the well with the same formation pressure. So the formation pressure equals 3000 psi is the pressure, okay, is the pressure exerted by the formation fluids within the pore space. Okay, so guys, for the formation pressure, scientists make some calculations for calculating the normal formation pressure gradient. And at this point, if your formation pressure gradient is 0.465 psi, so it will be normal formation pressure gradient. So let's see, for example, here our formation like this. Okay, so if you calculate your formation pressure at this point and divide your formation pressure over the TVD, okay, and the final result will be 0.465, so it will be normal formation pressure. If you found it is larger than this number, so it will be abnormal formation pressure. If it is below, so it will be subnormal formation pressure. For these calculations have been done, it will be done in water formation, okay. So here, as mentioned before, these are the situation. Here is okay for the formation pressure, but for any reason, our formation pressure become larger than the hydrostatic pressure due to, for example, abnormally pressure reason. So guys, now it's your turn to share with me how formations become abnormally pressure. Anyone could share the reasons for formation to be abnormally pressured? Guys, anyone could share? Okay.
Due to the compression temperature.
Sorry. Okay.
Due to the compression of the formation and temperature.
Okay. We have many reasons for the formation to be abnormally pressured. First reason is called undercompacted shale sand. If you look here, we have our formation like this. Okay. Due to the normal compaction, so we have dewatering process due to the compaction of this overlying formation. So the water tends to be out of the pore space. So here the water tend to be out of the pore space, okay, in a process called dewatering. But once we have a shale layer like this one, the shale layer is impermeable. Yeah, this one. Yes, the shale layer is impermeable formation. Okay, so the water can be able to move from downward to upward. Okay, no permeability for the shale. So water tend to be out from this area, from this area, but can't be able. Okay, so there will be trapped pressure in this area, as you're gonna see. Okay. Yeah. So here we have trapped pressure in this area. So if you're gonna drill a well in this area, we're gonna find abnormally pressure formation. So we may be in underbalanced situation. If you look here to this figure, you're gonna find the formation pressure tend to be increased in a normal increment, okay, in a normal increment, okay, due to increase in the depth. But once we found here the abnormally pressure area, we're gonna find a sudden shift. We're gonna find here a sudden shift for the formation pressure. Okay, let's adjust this point. Okay. Okay. So guys, that's what we mentioned. We have shear layer. Once the shear layer has been burned down like this, okay, so it causes trapped pressure in this area. So once reaching to here to the shear layer, we're gonna find a sudden shift for the formation pressure to be increased due to the undercompacted shear sand. And the undercompacted shear sand is the most common cause, for the abnormally pressure formation. Second reason is called gas gap rock. As you know, gas is lighter fluid, okay, and due to its lower density tends to move upward, okay. But here we have a sealing formation, cap formation or cap rock. This sealing formation acts like the shale, so no permeability. So gas can't be able to move upward further, okay. So let's take by calculation the effect of the abnormally pressure formation. Let's have here point number 1, here point number 2, and here is point number 3. So the one who, okay, please, Ahmed Tijani, make mute all the time, okay, not to make confusion for the other guys. So here we have point number 1, point number 2, and point number 3. If we need to calculate the formation pressure at all of these points, so formation pressure, let's say formation pressure at point number 1, P formation at point number 2, P formation at point number 3. If we have our TVD depth is about, let's say, 10,000 feet. So here as the middle will be 5,000. Here will be 5,000, same thing, same depth. And the remaining depth will be also 5,000 feet. Okay, so at the point number 3, at the point of number 3, it will be normal formation pressure. So it will be the gradient 0.465 times TVD 10,000. So it will be 4,650 PSI. Okay, if we need to calculate for point number 1, it will be the same thing, 0.465 times 5,000. So it will be 2,325 PSI. Okay, so what about at point number 2? Okay, the abnormally formation pressure 1. Okay, at point number 2, we have formula to be followed. P abnormal equal what? Equal P formation minus P gas. So P formation at this depth, okay, at the total depth as a TVD is equal to what? Is equal to 4,650. So here P abnormal pressure will be 4,650, okay, minus pressure of the gas. So the pressure of the gas we have here, gas pressure gradient is 0.1 psi per feet. So here 0.1 psi per feet times its TVD 5,000. So here 5,000. So now we have 4,650 minus 500. So now the result will be about 4,150. Okay, So let's imagine at the same depth at point number 1 as the same depth at point number 2. We have for the abnormally pressure formation 4,150. For the normal one, we have 2,325. Okay, so let's imagine the difference between the two pressures. At point number 2, it will be abnormally pressure. So we have normally the double of the pressure, okay, twice the pressure of the normal pressure. So if you're gonna drill a well here in this area, you're gonna find abnormally pressure formation, and you're gonna have a kick. You will be in underbalanced situation. Okay. Okay, let's go further talking about surcharged formation.
So, sorry, I didn't get the last point because.
Okay.
Yeah.
What's the problem?
Here, point number 3. Why you can calculate it as normal pressure at the bottom? Maybe
Yeah.
the gas has more pressure.
Yeah. Okay. Let's say here is the normal pressure. The end of the gas cap is here at this area. Okay. So here, this formation is normally pressure. If we have formation here, it's normally pressure. Then we have here the gas cap rock area. Then at the end here, we have formation pressure is normally. Okay. So the issue is in the middle. Okay. So we need to calculate the pressure here as a 0.3 as a normal formation pressure, So if you're gonna look here, once we need to calculate the pressure at point number 2, we take the whole pressure as normal. Okay. So the problem is when we have a gas, so there is a problem of the abnormally pressure. So if we need to calculate pressure at point number 2, we take the full pressure as a normal pressure, then deduct from it the pressure of the gas. So here at point number 3, no gas effect. So we're gonna take it as a normal formation pressure. Okay, to calculate, just put the constant times the TVD. For the point number 1, same thing, normal formation pressure, no gas effect. So it will be the gradient times the TVD. But for point number 2, we take the full pressure of the formation, pressure, minus the pressure of the gas. Okay, so it's clear.
Sorry, I know how to calculate, but why you take the pressure at the end is the normal pressure. So maybe the gas, this area has more pressure.
No gas at this area. If you look here at this area, gas cap, we have here cap rock. So cap rock allow no communication between gas and the upward of the cap rock. Is it clear? Let's imagine now. We have here cap rock. So here we have gas, no gas. So we make here at this point number 3, we calculate the formation pressure as a normal. Why? Because no communication between the gas and these layers. Okay, no communication. So the pressure here at this area will be normal pressure, no gas, no effect of the gas. Okay, no communication due to the existence of cap rock, no permeability. Cap rock formation, no permeability. So it will be always sealing formation. So the pressure here will be normal formation pressure. What's the point?
Yeah, thank you. I got it. Thank you.
Okay. Okay, another reason is called surcharged formation. For example, we may have here pass cement job after we running the casing. So we have lower layer and the upper layer. The lower layer always charging the upper layer due to the bad cement job. Okay, so if you're gonna drill a well here in this area, you make your calculation based normal formation pressure. So you expect the pressure here to be 3,000 psi. But due to charging up from the lower formation, you're gonna find a sudden jump for the formation once drilling. So it will be, for example, 3,500. So if you're gonna drill a well here in this area, you're gonna find a sudden jump about 500 psi. So you will be under balance and you may have a kick. Okay, so you need to take into consideration these parameter, surcharged formation. Another reason is called fault, and this fault is related to geological issue. Okay, naturally surcharged formation. Here we have our formation normally, let's say 3000 psi at 2000 feet TVD. Okay, once the fault happens, so some formation moves upward and some formation moves down. If we're gonna drill a well here in this area, so it will be normally pressure, okay, 3000 psi. But once the fault happened, so the formation moved to a shallower depth, let's say here at 1000 feet, okay, but with the same pressure, 3000 psi. So if you're gonna drill a well here in this area, okay, you expect the pressure to be lower than 3000, okay, due to a shallower depth. But at the shallower depth, you found a higher pressure, okay, so you're gonna find here a kick, okay, you will be in underbalance. So you need to take into consideration the fault reason. And last reason with us is called artesian well. Artesian well, if you look here, we have our rig level is at a shallower depth or at a lower level than a source of water. If you look here for the artesian well, you're gonna calculate or take always your TVD based on this section, TVD, but you ignore this section. So if you need to calculate formation pressure here, you need to calculate based on the full TVD, okay, not this section, okay? So once you make your calculation based on the shallower TVD, you're gonna have a lower formation pressure value, okay? So once drilling and reaching to this part, you're gonna find you will be in underbalance situation and you may have a kick, okay? So to overcome this issue, you need to increase your mud weight or adjust the level from the beginning. Now to talk about formation characteristics, we have two formation characteristics, two reservoir characteristics. Main two characteristics is porosity and permeability. So for the porosity is the percent of the void space within the rock. So for example, if we have our rock like this, the rock consists from grains and pore space. So the pore space is the space between the grains, like this. So here we can make storage for the fluid, okay, in the pore space. So the volume of the pore space over the rock volume is called porosity. So the porosity is what? Is the percent of the void space within the rock. Let's take or make comparison between two rocks, shale formation and sand formation. And sand formation. So at a depth of 10,000 feet, for example, here at this point, okay, if we need to record the porosity for the shale and for the sand, so we're gonna find here for the shale we have about 10%, but for sand we're gonna find it's about 20%. So this is a point we're gonna use the sand formation to act as a reservoir, not shale. Okay. Also nowadays we're gonna use shale for unconventional drilling. Okay. Why you're gonna use shale? Because it has no permeability, as you're gonna see. At the same depth here, guys, at depth 10,000 feet. Okay, let's talk about first about the permeability. If we have our well here, okay, and here is the grains of the formation. So formation fluids will moving from the area or the interconnected pore space till entering to the well like this. So the permeability is the ability of the formation fluid to move through the rock, or the ability of the rock to transmit the fluid through it. So if we need to make comparison between shale formation and sand formation at the depth of 10,000, same depth, so we're gonna find zero permeability for the shale. That's why you're gonna use that for conventional reservoir rocks. But for sand, you're gonna find it's about 0.5 Darcy, okay, and this is large number, okay, so it's about 500 milli Darcy. So in the reservoir engineering, it's a very large number. So a rock that is porous doesn't indicate that it's permeable, okay. You may have a porous rock but no interconnection for the pore space, so it will be impermeable. Now to talk about bottom hole pressure, static and dynamic bottom hole pressure. Here, the mud circulation system, we're gonna take the mud from the active bed via the suction pump to the mud pumps, then to standpipe manifold up to the drill string down, then up the annulus, then to the flow line, shaker, degasser, desander, desalter, centrifuge, settling tank, and back again to make the circulation again and again. So here, for static bottom hole pressure, static here means pump is not running, no pump is running. Okay, so here 0 SPM, 0 PSI. So bottom hole pressure here, if we put a gauge here as area, only calculates the hydrostatic pressure. So bottom hole pressure, in case we are static, only equal to hydrostatic pressure, mud weight times the constant times TVD. So here we have 5,200 PSI. Okay, so what about dynamic pressure? Dynamic bottom hole pressure, now we have pumps running. We have pump pressure is about 2,600 PSI and 80 SPM. Okay, so what is the pump pressure, guys? The pump pressure is the pressure required to overcome all pressure losses inside the system. So what I mean, here we have 2,600 PSI. Then while moving in the surface line, okay, we moving from left to right. So we have a friction pressure from right to left, 100 PSI. So now the remaining pressure is 2,500. While down the drill string, we losing 400, okay. Then at the collar, we losing 500, and the maximum pressure loss will be at the pit nozzle, okay. So it's about from 60 to 70% of the pump pressure. So now we only have 300 PSI at the bottom, okay. So to complete movement to be reaching to the flow line, we have 300 PSI to be lost in the annulus side. While moving from bottom to top, okay, we have a friction from top to bottom. It's called annular pressure loss. So if we need to calculate our bottom hole pressure in case pump is running, we need to take this pressure into consideration, this pressure loss into consideration, okay? So the fluid here moves from down to up, okay, or from bottom to top. So here we have a pressure loss from top to bottom called annular pressure loss, or OPL. So if we need to calculate the bottom hole pressure in case we are in a dynamic situation, in case we have pump pressure and pumps running, so it will be the hydrostatic pressure at the static plus the dynamic one, the effect of an APL, annual pressure loss, 300 PSI. So now the bottom hole pressure will be 5,500 PSI. This increase due to the effect of the annular pressure loss affecting downward. Okay, so here different situation for bottom hole pressure. In case we are in static, so bottom hole pressure will equal to the hydrostatic pressure. In case we are in a circulation, we have pumps running, so bottom hole pressure will equal to hydrostatic pressure plus APL, annular pressure loss. In case we are circulating with a rotating head, for MPD, managed pressure drilling, or for underbalanced drilling, so here we have circulation with rotating head. So bottom hole pressure will equal hydrostatic pressure plus APL due to pumps running plus back pressure from rotating head. For kick circulation, now pump is running also, and we have a choke. So bottom hole pressure, we have hydrostatic pressure, APL due to pump is running, and a choke pressure due to the effect of the choke. Okay. Here is the comparison between static and circulating. If we are in a static situation like this, so bottom hole pressure here will equal the hydrostatic pressure, 10 ppg times TVD 10,000 times constant of 0.52. So we have here 5,200. In circulating system, so we have the plus factor, APL, annular pressure loss. So bottom hole pressure will be 5,450. If we have formation pressure is 5,300, and here same thing, 5,300. So we're gonna find while we are in static, we are in underbalance, so formation fluid will enter to the well. But here, once the pump is running, so we have additional overbalance about 150. So no formation fluids will enter to the well. So here formation will kick, and here formation is under control. Okay, the effect of APL came to have a new concept called equivalent circulating density. While we are in static situation like this, no pump is running. So here we have, let's say, our mud weight is about 10 ppg. So bottom hole pressure is equivalent to 10 ppg. But once pump is running, okay, same mud weight, we have here mud weight is 10 ppg. Okay, and the pump is running like this. So bottom hole pressure here, feel the pressure equivalent to, for example, 10.5. Why is this increase? We have the same mud weight inside the well. Mud weight didn't change, okay? So what is the difference? Why bottom hole pressure reads more equivalent pressure, 10.5 ppg? This is because the effect of an APL. Once the pump is running, so there is additional factor APL acting on bottom, okay? So this is theoretical increase in mud weight, no actual increase for mud weight. So here, the APL or annual pressure loss where circulating has the same effect on the bottom hole pressure as increasing the mud weight, but no actual increase for the mud weight. So the theoretical increase in the mud weight plus the original is called equivalent mud weight or equivalent circulating density. So how to calculate the ECD or equivalent circulating density is equal the original mud weight, 10 ppg for example, plus the APL value, 300 for example, over TVD if we have 3,000 feet times constant. So let's calculate. Let me try with you. So it will be, let's say, 10 ppg plus 300 over 0.52 times 3,000 feet. So it will be 11.92. So now, guys, the answer will be 11.92 ppg. That's why because the effect of APL or annular pressure loss. Clear, guys? Clear, guys?
Yes, clear.
Okay. So now let's talk about the effects on pump pressure. Now we have here, yeah, let's say, yes, here's this point. Okay, so what is here? No pumps running here. Okay, so let me try to share from increase the mud weight. Okay. Okay. So guys, for the first part, if we make a change for the mud weight, okay, if we have, for example, mud weight is 10 ppg and we need to increase it into 11 ppg. So what do you think for the pump pressure? It will increase, decrease, or stays the same? If we have pump pressure from the beginning, it's about 2,600, okay, and we need to change the mud weight from 10 ppg to 11 ppg. You think the new pump pressure will be higher, lower, or stays the same? Anyone could share?
Increase.
Yeah, it will be increased. So how to calculate the new pump pressure? New pump pressure here equal the old pump pressure times the mud weight new over the mud weight old. So let's have by calculation. Here is the old pump pressure, 2,600 times 11 ppg, the new mud weight, over 10 ppg, the old mud weight. So here we have 2,860 psi. So guys, if we have, for example, the final result is 2,860.3, okay? We need to have this pressure as integral number. So we may round up or round up. Both are okay. So here it will be 2,860, it's okay. Or if you make it 2,861, so it's okay also. Okay, just round up or round down for this pressure. Okay, so here the second part. If we make a change for the pump speed, so let's say, for example, we have the current SPM or the current pump speed is 80 SPM stroke per minute, and we need to increase it to 100 SPM. So what do you think, guys, for the pump pressure? It will be increase, decrease, or stays the same? If we changing the pump speed, what do you think for the pump pressure? Increase, decrease, or stays the same?
Increase.
It will increase.
Yes, it will increase. So how to calculate from this formula? New pump pressure equal old pump pressure times SPM new over SPM all power 2. And don't forget for this power 2. Okay, so here for this example, if we increase the pump speed from 80 SPM to 100 SPM, okay, so here is all the pressure, 2600 times 100 over 80 all power 2. So the answer would be 4,063. Okay, and same thing, if we have the final answer 4062, for example, 0.9, so we may round up, so it will be 4063 or 4062. Both are okay. Okay, now to talk about the key occurrence. Okay, here we have reasons why formation pressure exceeds the hydrostatic pressure. Two main reasons. First part is pore pressure increase, and this one we talk about it. Okay, when we talk about for the abnormally pressure formation reasons, we have many reasons. First one is under compacted shale sand. Then we have gas cap rock. Then we have fault formation, surcharged formation, and artesian well, and many more reasons like salt domes, like tectonic movements, like. Okay, so here we have our formation pressure for any reasons, formation pressure to be have a sudden jump, to be abnormally pressure. So now formation pressure will be larger than hydrostatic pressure, so will be an underbalance situation, so we're going to have a kick. The second part for the hydrostatic pressure itself, if the fluid column reduced. Okay, so let's see here some cases to have influx. First one, insufficient drilling fluid density. Insufficient drilling fluid density. For example, if we running the centrifuge too much time, so we're gonna remove more solids from the mud, so we're gonna dilute it, and the mud density will not be sufficient to be used in the wellbore. Also, if we line up for the water tank, so we're gonna make dilution for the current mud weight, for example, from 10 ppg to be about 9.5, so you're gonna be in underbalance situation and you may have a kick. Number two is drilling fluid cut or gas cut. Drilling fluid cut or gas cut means we have gas percent in the mud column. Okay, once the gas enters to the well, it has no effect at the first instant, no effect for the gas. But with time, with circulation, like this, gas volume will be increased, and this increase in gas volume will make reduction for the hydrostatic pressure and will also make reduction for the bottom hole pressure. So we will be in underbalance situation and we're gonna have influx. Number three is lost circulation. Lost circulation, it means you lose some mud weight inside the wellbore or inside the formation pore space. Okay, so guys, is all lost circulation situation lead to have influx? Anyone could share? Lost circulation. All lost circulation situation lead to have an influx?
No.
Yeah.
No, because if we get lost in one formation, we cannot get influx from the same formation. We have to get influx from another formation, I think.
Yes, but here it depends on the level you drop. For example, if we have here our mud level at this point, okay, if we have losses here, then the mud level become at this stage, okay. So if the hydrostatic pressure is still sufficient to be over than formation pressure, so no influx from the formation. But if the level, for example, dropped to this level, okay, then the hydrostatic pressure being lower than the formation pressure, so you're gonna have influx. So loss circulation material, loss circulation situations, depending on what?
One thing, but the hydrostatic pressure cannot drop less than formation pressure, because
Why?
formation pressure will push the mud. So how come you can get loss and get influx from the same formation?
No. For example, if we have here, let's say formation pressure 3000 psi, okay, and you drill here with your mud weight to be overcome, so give you hydrostatic pressure, for example, 330, okay, 3300 psi. If you frag the formation here, or there is a C formation here or loss zone here, so your hydrostatic pressure will be invade this formation, okay, invade this formation, C formation or low pressure formation, okay. So the 3300 psi, okay, will be dropped to a value lower than this pressure. So if the hydrostatic pressure is dropped to, for example, 3100, so it's okay. We still larger than the formation pressure, so it's okay. We are overbalanced. But if we lose more fluid here in the formation, in a C formation, so our hydrostatic pressure will be dropped larger. So it will be, for example, let's say 2900. So now we are lower than the formation pressure, so we're gonna have influx. So,
but I mean, we cannot get influx from the same point when we lose and when we get influx.
okay, I mean. Yeah, you will not get influx from the same formation.
Yeah, that's what I mean.
Yes, we have formation. You lost fluid in it, then you're gonna have influx from the higher formation pressure formation. Okay, so the sequence of the formation you drill, for example, like this. Okay, here, let's say we have here low pressure formation, this one, low pressure formation. So you make your hydrostatic pressure calculation or your mud program, okay, to have 10.5 ppg. And this formation is equivalent to about 8 ppg. Okay, and then increase to be 10 ppg. So while drilling this sequence of formation, once reaching to the low pressure formation, this one, we're gonna have losses. 10 ppg is larger than 8 ppg, so you're gonna make induced fracturing and lose mud weight. Okay, once losing mud weight here and complete drilling to the further formation, so you're gonna face here 10 ppg, and you already lose some fluid in this formation. So if your hydrostatic pressure in this situation or the level drop in your hydrostatic pressure is not sufficient to be still over 10 ppg, so you're gonna have influx. Okay, reach it.
Thank you.
Okay. Then for number 4, here, failure to keep all full. And this is the responsibility of the driller all the time. All the time during pull out from the well, the driller need to make comparison between the actual volume from the tank and the actual the calculated volume, and all the time need to compensate for the mud reduction, mud level drop due to pulling out from the well. Okay, so if the level drop to a specific value that allows the hydrostatic pressure to be lower than the formation pressure, so you're going to have influx. And number 5, we're going to talk in the next slide, swabbing and surging while tripping. Swabbing, like the suction effect while pulling out of the hole. If you pull out so fast, so you're going to allow your hydrostatic pressure or bottom hole pressure to momentarily reduce, so you're going to have influx. And surge is vice versa. While running inside the well, running the hole, you may add some pressure to the bottom hole, so you may cause induced fracturing, and your hydrostatic pressure dropped, and you may have influx. For transition zone is a change in the formation pressure. So once you are drilling a formation and you notice, for example, your ROP rate of penetration has a sudden jump, for example, from 45 feet per hour to be 46, 47, 50, 55. Okay, so this may be indication you have been transferred from normal formation pressure to abnormal formation pressure, so you need to make flow check. Okay, and this is what we're gonna talk about here for surge and swab. If you look here to this figure, while pulling out from the well, we may cause here a suction effect. So this suction effect allows the bottom hole pressure to be momentarily reduced. So if your bottom hole pressure is still above the formation, no influx. If your bottom hole pressure is less than the formation, so you're going to have influx. Here for surging while running in the well, you may add some pressure to the formation, causing some fracturing. So here bottom hole pressure, okay, increase to a value that causes fracturing here in the formation. So you lose mud in the formation. So your hydrostatic pressure starts to decrease due to the reduction in the level, due to level drop. Okay, so now our bottom hole pressure, if it is lower than the formation pressure, so you're going to have influx from the formation. So let's talk about the reasons. Here, swell pressure is a momentary reduction in the bottom hole pressure. The reason, if we pulling the string too fast, if we have small clearance or narrow annulus, so the mud can able to return to its normal position. If we have cold bed or cold stabilizer, same thing, the mud can be able to return back. If we have high gel or high viscosity mud. So how to identify if we have swab or not? You can identify from incorrect fill-up. You need to make a comparison between the actual volume taken from the trap tank and the calculated volume based on you dry trapping or you make wet trapping. Okay, if there is difference between the actual and the calculated volume, so you need to make flow check. If the flow check no flow at the surface, so if it's the negative, you need to run back to bottom and circulate bottom up. Why run back to bottom and circulate bottom up? Because we may have some gases just enter to the well. Okay, so we need to circulate them. Okay, but if there is a flow, so we need to shut in the well immediately without any delay. Let's talk to the surge. Surge is vice versa. Here, momentary increase on the bottom hole pressure, running strength too fast, small clearance or narrow annulus, cold bed, cold stabilizer, high gel, high viscosity mud. Here for wet and dry trapping, if you look, for dry trapping, we only hear out from the well with the metal displacement only, no mud inside the pipe. Okay, no pipe capacity is included in our calculation. Okay, so it's called open end displacement. Always the mud returned back from the drill pipe. But here for the wet trapping, you are out from the well with the metal displacement, this one, plus the pipe capacity, the mud inside the pipe. So here the pressure or the level drop for the hydrostatic, okay, or for the mud will be larger, okay. So this is called close-end displacement. Why close-end displacement? Because here no mud can back again to the wellbore. Okay, so here just a representation of the dry tripping and wet tripping. For dry tripping, you only take into consideration the pipe metal displacement parallel per feet. But if you are in a wet tripping, so you need to take metal displacement plus pipe capacity. This one is called metal displacement, and here's the inside of the pipe is called the pipe capacity. So for example, if he mentioned you need to pull out 3 stands from the well, so you need to take number of stands times length of stand, for example, 93 feet, times the depending on the wet tripping or dry tripping displacement. So if he mentions that you are dry tripping, so you need to take only here the metal displacement, this number 00764. If he mentioned you are in a wet tripping, so you need to take the summation of metal displacement and pipe capacity, this one close-end displacement, so you need to take 0254 to calculate. So this one for dry tripping and this one for wet tripping. Okay. Okay, here is the trip tank. The trip tank has some specification or features. Trip tank is a small tank with a capacity from 20 to 50 parallel. Trip tank used to fill the well and take return back to the tank. Level drop while tripping out. Okay, why? To compensate for the level drop and increase while tripping in. So for example, if we are pulling out from the well, so the suction pump here start to take fluid from the trip tank and start to compensate inside the well, so the level here will drop. If we run in the well like this, so we're gonna add some mud, okay, due to the pipe displacement or the if we are close-end displacement. So we have here return line to take the return fluid again to the trip tank. So here level drop while tripping out because you take fluid from trip tank to compensate inside the well, and the level increase while tripping in because you take return from the well to the trip tank. If you look here, this is the starter volume. We're gonna start with 15 parallel. Okay, this is starter volume. We make pulling out from the well, so we start to fill out from the trip tank to compensate here inside the well. Okay, so after we pulling some stands from the well, the finished volume is 10 parallel. So the actual volume taken from the trip tank is about 5 parallel. Okay, so you need to compare this actual volume from trip tank and the calculated volume you already calculated. Okay, if you are dry tripping or wet tripping, okay, and make comparison between the actual volume and the calculated. If no difference, so it's okay. If there is difference, so you need to make flow check. You have swab. Okay, so here number of stands, then here actual mud volume from trip tank, and here is the actual, the calculated volume based on wet or dry tripping. If no difference, so it's okay. If there is difference, so you need to make flow check. You have swab, okay? Flow check. If no flow, you need to run back to bottom and circulate bottom up. If there is a flow, so you need to shut in the well immediately without any delay. Okay, so to allow your system to be pulled dry, to have free section here, we need to start pumping heavy slug. Okay, so let's say we need to pump about 30 parallel heavy slug. If we have here the normal mud weight and the drill string and in the annulus is about 10 ppg. So we need to pump heavy slug, let's say 11 ppg. Okay, so once we pumping 30 parallel, we have here on the trip tank 30 parallel. Then we make disconnect for the TDS system. So now, due to the high weight of the heavy slug, detubing effect will happen. Okay, this one is heavy, so detube effect will happen. So we have here additional increase in the trip tank. Why is this additional increase? Due to detube effect. So he may ask you in the Wellsharp questions about how much increase, how much is the additional volume on the trip tank. So you're gonna calculate for the additional volume only, okay, due to detube effect. Or he may ask how much is the total volume. So let's say if we have additional volume here to parallel. So if he asks about the additional volume, the answer will be to parallel. If he asking about the total volume, back again to the trip tank, so you need to take the full volume of the slug, 30, plus the additional volume 2. So the answer will be 2 plus 30. So it will be 32 parallel. Okay, as long as the slug is still inside the pipe, so the bottom hole pressure here, bottom hole pressure will not change. Okay, but once the slug is displaced into the annulus, once the slug started to enter the annulus, so now bottom hole pressure will start to increase. Why? If you look here to this figure, okay, here we have higher mud weight, okay, but less TVD. And here is the low mud weight, but full TVD. Okay, according to the hydrostatic pressure equal constant 0.52 times mud weight times TVD. So for the drill string side, we have higher mud weight and less TVD. So there's compensation for these two factors. So hydrostatic pressure is okay. But here for the annulus side, we have higher TVD and lower mud weight. So it's okay, it's balanced situation. So bottom hole pressure here is okay, no change. But once this slug started to be displaced here into the annulus, now we have increase in the mud weight and we have the same TVD. Okay, so now bottom hole pressure will be increased. So as long as the slug and the drill pipe side, no change for the bottom hole pressure. Once the slug is in the annulus side, started to be displaced into the annulus side, so now bottom hole pressure will be increased. So it's useful to pump heavy slug before tripping to allow you to have free section of the pipe empty, so you can pull dry. The bottom hole pressure is not reduced as the heavier mud will compensate for the empty pipe. The bottom hole pressure will start to increase when the slug starts to exit the pipe. Okay. Now we have something called self-fill or auto-fill casing float. The conventional casing float, conventional, okay, not self-fill. The conventional casing float, you need to fill your casing string all the time from the surface. Every substance fill, every substance fill, every substance fill, okay, and make close-end displacement. But here, to make fast stripping, okay, you need to run with self-fill. Self-fill is like this. You run your casing with here self-fill. So once you are running inside the well, the mud enter the casing. No need to fill the casing string from the surface. You run with your casing string empty, and once down the well bore, you have mud enter to your casing string. So you have a return on the trip tank equal to the metal displacement, only the metal displacement of the casing string. Okay, so here, how to know the self-fill is working properly? You're gonna find metal displacement on the trip tank. But how you know if your self-fill here is blocked? You're gonna find close-end displacement, the metal displacement plus the pipe capacity or the casing string capacity. Okay, everything has advantage and disadvantage. So for the advantage, no need to fill the casing from the surface. you just run with your casing string empty, and once entered to the well bore, you're gonna find your casing string started to be filled, so you can make fast tripping. But the disadvantage, if you have influx, okay, if you have kick, so the kick will enter to the casing, okay, as the self-fill doesn't make difference for the normal fluid mud wave and the influx, okay. Once we reach into the setting depths of the casing setting depths, we need to convert this self-fill into check valve. So we down pull from the surface, so we can push, okay, or pump cement, so cement can move into the annulus and prevent the back movement of the cement. Once we fail to convert the self-fill into a check valve, so cement will you back into the casing, okay? So the disadvantage, kick will enter to the casing. It fails to convert to a check valve, so cement will tube inside the casing. Okay, guys? Clear?
Okay.
Okay. What? Anyone has question? Okay. You need a break or go ahead?
Can
Yeah. You need a break. You need a break now or go ahead?
yeah, it's better.
Break is better.